Hello and good late afternoon and evening here where we are. My name is Markus Pössl. I'm part of the Max Planck Institute for Astronomy, also of Hours of Astronomy, and I'm also the International Astronomical Union's National Outreach Coordinator Deputy for Germany. So I'm glad that you could join us here for the 100 Hours of Astronomy, which is an event by the IAU's Office for Astronomy Outreach. And we'll go straight ahead. I'm being joined by three young astronomers today, youngish astronomers today, with three very interesting to me different topics. So we'll dive right in. I'll just ask Lucian Seeburger to join me here on stage. Hello, Lucian.
Nice to be here.
Yep, you are. Let's hope that the connection holds up. You are a little bit chopped off. So can you say just a few sentences about yourself to start with?
Yeah, so as I introduced, I'm Lucian. I'm a PhD student at the Max Planck Institute of Astronomy. I've done research in all sorts of different areas, and recently I've actually looked into what we call astrobiology, which is researching life and stuff concerning life in outer space. Very
okay, and we know that that is a topic that many find very interesting, and rightly so. So I'll just hand this over to you, and I hope that all of us enjoy this talk.
As Marcus about how we can find a thing to do. Planet has been a question on the mind of humanity for a really long time. Just look at popular media results in all different sizes and forms, but actually aliens, if they were to exist, in discover lots and lots of new planets or
Lucian, I'm afraid I have to cut you off here, but your current connection is not sufficient. We can't hear your talk, which is a pity in particular because the slides, as anyone can see, are really nicely done. But I'm afraid without the audio, we have a problem there. So I'm afraid that I'll have to cut you off. Maybe you can find a way of improving your connection. Maybe there are still some flatmates that you can throw out of the internet to improve. But as it is right now, I'm afraid we will move on to Jana. To Gregor next. So far. Okay, so I'll ask Gregor to join me on stage. So,
hello, everyone.
Hello, Gregor. Can you introduce yourself with just a few sentences?
Yes. I am a postdoc at the Max Planck Institute for Astronomy here in Heidelberg, and I work on the Euclid Project.
And you're going to tell us all about what the Euclid Project is.
Yes. So
right now. So
yes,
this stage is yours.
Thank you. So I will try to spend a relatively large arc from the mission of Euclid to my specific topic, which is simulating images. And I will start saying what Euclid is in principle. So it's a space telescope. The mission is to get constraints on dark energy, which is one of the biggest puzzles in the universe today. So dark energy, if you assume our current cosmological model, accounts for about 76% of the energy in our universe. So by far the largest fraction. And we don't really know yet what it is. So the effect that we can observe is that the universe seems to accelerate away from us, and that only in recent times. So in the figure in the bottom right, you can see that the universe started out with a big bang, expanding, then decelerated, and recently started, due to dark energy, to accelerate again. So Euclid is launching, if everything goes well, early 2023 to the Lagrange 2 point, which is always on the far side of the sun from the Earth, about 1.5 million kilometers away. And it's a large survey mission that should observe about 37% of the sky. So it has 2 probes. One probe is tomographic weak lensing. So weak lensing is one form of gravitational lensing which describes the light deflection by masses in the foreground of some background galaxies. So if you have here these images of galaxies where I put some circles in for reference and you move a point source, a point mass in front of it, you see that due to deflection of light, the shapes are distorted. And of course, the effect we actually observe in weak lensing is tiny. It's by far not as large as this. And also what we have to take into account is the distances of galaxies, because that changes where the light ends up when we project it through a foreground mass towards them. So we use models like this where we have basically distance measurements and then try to infer from the shape measurements of galaxies how mass in the foreground is concentrated. And it gets a bit more complicated because each galaxy also has an intrinsic shape. You need to average over many galaxies, then produce the distortion of these averages, which you see represented here as these little sticks in the images. And from these, we can infer something about the mass distribution. So with this mass distribution in 3D, so also in the line of sight distance, which is in astronomy the same also of going back in time, of seeing the evolution in time, we can actually infer something about the impact of dark energy on the cosmological structure. The other probe I will not really talk much about. It's called Barionic acoustic oscillations. So what we observe is essentially overdensities of galaxies that evolve also through time, through precise position measurements and line of sight distance measurements of many galaxies. And the effect that causes these overdensities is a plasma wave in the first period of the universe. So it traveled through the plasma in the universe when it was less than about 370,000 years old, when it was about 1,100 times smaller than it is now. So the problem is, as you can imagine, the signal in both of these probes is very faint. So if we don't have a very detailed understanding of all systematic effects of the instrument, of our sky, of foreground contributions, it's not possible to really infer much. So there are a lot of people, which you see here in this image in the Euclid project, who develop software and who think a lot on how to extract from these probes cosmological measurements. So the idea is the following. We assume a description of the universe in some parameters, which one could call the cosmological model. Then you run simulations, you produce simulated catalogs of galaxies. You also have simulated stellar catalogs, you have an environment model and telescope model. And from all this, you produce images that are then processed as the observations would be processed to infer something about cosmology again. And hopefully this matches what you put in the input simulations. So since one image is supposed to be about the same worth as 1,000 words, I have the equivalent of about 6,000 words here at least. I hope this is more useful. Again, you go from a few parameters, you produce cosmological simulations, which on the left you see are these structures of overdensities and connecting filaments between galaxies. Then you combine it with the Milky Way model, which is on the bottom left, with a model of the, in this case, background in the solar system, something called zodiacal light, and an instrument model to produce the images, which are in the center bottom. Then with a lot of computational power and the input of many people, you go back to the cosmological parameters. And if this doesn't work out, and we do actually run challenges to see if we can close this loop, then more development is needed. And of course, we have made sure that the instrument is actually capable to produce images in high enough quality that it is actually possible to close this loop. So now I'm going to talk about what you in this slide here see in the center image, the photometry near infrared images. And I'm going to talk about some of the most important effects in astronomy when you produce these image simulations, or also when you look at observations, the kind of effects that go into that. So this is one focal plane as observed in the near infrared by the Euclid instrument. It's, as you can see, it has 16 detectors. Each of them has 2040 times 2040 pixels. And if you zoom in, you can see that in this one focal plane, there is a lot of detail. But there's also all kinds of noise contributions. So as an example, I have here just a simulation of a tiny 100 times 100 pixel part of the sky with the same instrument. And this is noiseless and it looks absolutely perfect. So now we can start seeing what happens when we add different effects, instrument effects to it. So first we have noise, photon noise. So there's an average amount of photon that ends up on each pixel. But since each photon is independent from each other, the number of photons that arrives at any given time actually varies according to the Poisson distribution. And you get noise from that. Then you also have a background flux, which comes partly from the solar system, from light that is reflected back from dust in the solar system. So light from the sun that the dust in the solar system reflects back into the instrument. Then the detectors, they don't have perfect quantum efficiency, which means that the same number of photons don't always equal the same number of electrons or charge that's produced in a pixel. So some pixels, for example, are dead, which is this black area that you see on the left, where photons arrive and no charge is produced. So this is, I choose actually a very specific bad part of the detector. Most of it looks much better. Then also we have dark currents. So there are pixels which produce a lot of charge independently of the number of photons that end up on them. And this causes these white spots that can appear on the detector. Then we have readout noise. So this is just a relatively small constant noise contribution when converting the charge to actually digital information that you work with. Then these white dots, these are cosmic rays. So we are in space. There's no atmosphere to protect the instrument from high charge particles zooming through the universe. And they also end up on the detector and are detected. We have something called interpixel capacitance, which is a coupling of pixels to its neighboring pixels. So some of the charge is not only in the pixels where the photons landed, so it's transported a bit to the pixels next to it. You have some nonlinearity. It's hardly visible here. It's actually not a big effect. And this is close to what your final image is already. Sorry. So I have one last slide, which is something you get only for these infrared detectors. Sorry. And the sorry. So you see that for cosmic rays, you actually see how they produce errors in the pixels that you can measure. So for each pixel, you also have a data quality map, and this allows to help a bit to remove some of the artifacts. And that's all. Thank you.
Okay, thank you, Gregor, for that. We do not at this point have any comments in the chat, so if you're viewing this either on YouTube or on Facebook, feel free to ask questions and post comments in the chat and in the comment section. So we have an eye on this, and if there's something that we can answer, then we'll pass it on. So we are going to have later on a possibility for asking general questions. So just know that this section is there. Okay, so Gregor, thank you, and we'll talk later on when we sort of form a panel. And next up is Jana. So thank you for joining us, Jana. Tell us a little bit about yourself.
Thank you for inviting me. I'm Jana. I'm a postdoc at Max Planck Institute for Astronomy, and my biggest passion are the galaxies, the most distant galaxies of the universe, and their evolution. And today I'm going to talk about them. So
Okay.
Let's start.
Yes, so let me just sort of add you in, and then the stage is all yours.
So once upon a time in a galaxy far, far away. This is a beginning of a story which many of us heard. But what do we mean when we say that a galaxy is far, far away? How far away it is, and actually how to find these galaxies and how to observe them. Let's first go a bit closer to the Milky Way and look at the closest galaxy. And this is Andromeda Galaxy. It's our nearest neighbor. And it's one of the galaxies which we even can see with a naked eye if we go to a sufficiently dark place. Unfortunately, it's now very difficult to find in the time when in the cities we always have a lot of light pollution. But this was probably the first galaxy people actually saw on the sky. And this closest to us galaxy is already at the distance of 2.5 million light years. How to imagine this big number? This is how much one light year is in kilometers and in miles. It's also even harder to imagine how big this number is. But let's imagine that we would go around the Earth, just around the equator, and we would just decide that we want to walk as many times that we would just walk for 1 light year. And in that case, we would have to go around the Earth for 8.2 billion times. And this is a lot. Even if we would do it just during 1 second, the whole circle around the Earth, we would need around 260 years to do that. And this is not possible to do for a single human. So actually, and now if you imagine that it's the distance 2.5 million times bigger, it's a very huge distance. And that's why intergalactic traveling is a very ambitious dream. Also, at some point, Andromeda is going to collide with the Milky Way and make this task easier. But it's not going to happen soon. But of course, there are many more galaxies in the universe. And astronomers made a lot of ambitious projects to find as many galaxies as possible. For example, these are the results from the Sloan Digital Sky Survey, which was made with the goal to observe galaxies and measure the distances to these galaxies to make a map of the universe. In fact, the results from the survey is a 3D map of the galaxies, but here you can see a 2D projection of this map. Each point shows the galaxy at its position on the sky and the distance. And the radius of this whole sphere is already 1.9 billion light years. But what's really interesting is that when we obtain this image, these galaxies put at the appropriate distances at positions on the sky, we can see the large scale structure of the universe. And this structure of the universe is very similar to the results from the simulations. So, for example, if we just look at how the matter in the universe creates the structure, and then the gas follows the dark matter, we can see that the galaxies that are formed in the simulation, they are distributed in a very similar way to what we observe. But we can go to even higher distances. And this is, of course, even more challenging task. The problem is that we need to collect enough photons from the galaxy, and the number of photons coming to us from the most distant galaxies is much smaller. So we need to take a lot of time to collect these photons, and that's why it's if you saw previously, like we observed a large fraction of the sky, but when we go to higher distances, we can only observe smaller fraction of the sky. So for the brightest galaxies, we can find them in a very large area, but for the faintest, we can only find them in a very small area. And that's why sometimes we compare the surveys of galaxies with the wedding cake, because they kind of have this structure. We first make a large survey of a large portion of sky, and then we go deeper and deeper in smaller areas. So how small these areas can be? Here you can see a very small region on the sky, which is shown here with a rectangle, and it shows the size of this area compared to the size of the moon. And this is probably one of the most studied regions of the sky. It's small, but it's extremely deep, and it's called Hubble Extremely Deep Field, because it was observed with Hubble. And this is how it actually looks like. This was the image obtained by Hubble, and believe it or not, it contains thousands of galaxies. And the closest to us galaxies are bigger and brighter, and we can see spiral arms, we can see some elliptical galaxies. They're all beautiful and diverse, but the most distant galaxies are just tiny little dots barely visible to us, but we can still find them on this image. And the faintest ones are 10 billion times fainter than the capacity of the human eyes to detect light. So we would never be able to see them unless we would use this very innovative technology on telescopes in space. But for the Hubble, it took 23 days to actually obtain this image. This seems like a long, but it's nothing compared to the time the light needed to travel from these galaxies to reach us on Earth, which is 13 billion years. And now you think that if the light traveled from these galaxies for 13 billion years, then probably the distance to these galaxies is 13 billion light years, right? But it's actually more complicated than it is, because as we heard before, the universe is expanding, and it's expanding at accelerating rate. So the light, like now, at this present moment, these galaxies are already more far away than they were at the moment when they emitted this light. And now they're at distances of around 31 billion light years away. So it's very distant galaxies. We cannot really reach these galaxies. Why do we care about them? And the reason for that is because we can study the evolution of galaxies and the evolution of the universe. We can take snapshots of different cosmic epochs and see how the galaxies looked like 13 billion years ago, 12 billion years ago, and just trace the evolution. And this is the main purpose of the work I'm doing. And maybe you've heard that the age of the universe is 13.7 billion years. So now you probably think that these galaxies are very young, at least less than 1 billion years old. Are these galaxies the first galaxies? And the answer is that most probably not. We still expect to find even younger galaxies and galaxies which are even more far away. But because it's a very challenging task, even more challenging than it already is, we need more new instruments. And this year, we are all waiting for the launch of the James Webb Space Telescope, which will help Hubble to go even deeper and to find these even younger galaxies. So there are going to be even more exciting signs in the future. So what it is, a galaxy far, far away? It's definitely so far away that we would never really reach it, but luckily we can look at it and see it and define its history. And interestingly, if there are any aliens in these galaxies, they probably see the same picture, maybe a little bit different, but the same, and they see us, but how we were 13 billion years ago. So thank you very much. This is the end of my presentation.
So thank you, Jana. And I think we all agree that we and those aliens really need to compare notes, because they know a lot more about our past and we know a lot about their past.
Yes.
Okay, so just a quick housekeeping note. Lucian, who was the one who had the trouble connecting, is now hopefully in a taxi on his way to the Institute. So very laudable on a late Friday afternoon. So hopefully he's going to join us from there in a few minutes so that we can hear his talk. And we will go to the... So Grega, I think you have to unmute yourself because you chose to mute yourself. So
yes,
we'll go on to the little panel discussion that we had planned. And since this is about astronomy in general, it's also about how do you become an astronomer. And so I would really like to know from each of you, how did you get into astronomy? What made you choose that particular subject? Maybe Jana can start.
Yeah, so I think it's a very long story, because it started when I was very young and I started to read books about science, and I was very fascinated that there is so much we can learn about the world. And I thought that this is definitely what I would like to do. I want to just explore the world and try to understand it in more details. But I was for quite a long time not really sure if I want to study math or if I want to study physics or astrophysics, or biology. There are so many interesting areas.
Some people might also say that if you want the details, then you need particle physics.
Yes, sure. But I still I read a lot about astronomy, and when I changed the school, one of my teachers who was teaching physics, she actually studied astronomy herself, and she kind of inspired me to follow this path. And I started to participate in astronomy contests between the school students, and then I started to study astronomy in the university. And since then, I'm continuously just studying, doing research, studying. You cannot do research without studying. It's like research is the path for studying for your whole life.
But it's fun, isn't it? I mean, you always learn something new.
Yes, I think that's probably one of the reasons why I think it's really amazing to be a scientist, because you will always learn something new, and I think it really gives some purpose of life to know that like you are learning all the time and you are discovering new things.
Very nice. So next we'll ask Gregor the same question. So how did you get into astronomy?
So similar than for Jana, actually, my interest in physics started relatively early. So when I was a kid, maybe 8 years old or so, my father tried to explain different phenomena, and I became interested in math and physics and astronomy. I read a book called Einstein's Universum in German, which was the first book that really made exposed me to cosmology, let's say. And this interest has stayed with me through my school time, certainly. Then I started physics, and actually I wasn't sure at the end whether I should go into astronomy or whether I should go into particle physics, because both seemed very exciting to me. And I thought one of the main drivers probably for me was to try and understand something fundamental about the physics, or how things work at a very basic level. And then it was a bit random. So I was looking around for diploma thesis at the time, which now would be a master. And I got one with Matthias Bartelmann, and that was astronomy. So
Okay.
I have stayed there ever since. And I must say what Jana said, it's true. So especially talking to colleagues and listening to seminars of what's going on, it's a joy to see how we make progress. And I think it's very unlikely for someone to make a huge impact like Einstein did with general relativity, for example. I mean, these are very rare moments, and I think Einstein also stood on the shoulders of giants. So there was a lot of work going on before his discoveries that enabled him to build this theory, and also on mathematics, actually. He couldn't do it without some new mathematical concepts. And I think even all of us doing our little topics, we contribute to the big picture. So that's what I enjoy.
No, and that sounds great. And I don't want to diss the particle physicists, but if I look at what is going on there in the past, let's say 20 years, and in astronomy, let's put it positive spin on it. I mean, there's been really exciting developments in astronomy as new telescopes come online. So, yeah.
Yeah, that was actually for me another reason. It seemed to be that the highest energy scales they cannot be approached with particle accelerators. They can be approached through astronomy nowadays.
Okay, so we'll go to Lucian.
Yeah, hello.
I'm glad to see that you have found a good connection.
Apologies for that. Yeah.
Again, so how did you get into astronomy?
I think similar to from what I hear for Gregor and Jana, I've been very interested in the sciences for a long time. There was actually, when I was 6 or 7 or so years old, there was a lecture series aimed at laymen, but adult laymen in my city, and my dad took me every evening. And it was once a week, every evening. And it was actually really lovely. And I was the youngest person there by far, but there was so much discussion to be had. And, that was sort of one of the points where I decided I'm going to go into science. And actually, when I went to university, I started studying physics. But I had a lecturer in first year I took an optional course in astronomy, and the lecturer was absolutely amazing. She was spirited. She was, she communicated that wonder about the cosmos and that desire to sort of put it all together and extract knowledge from these really far away, really big, really weird objects, stars and black holes and all of that stuff. And I think I was just really intrigued by that, by the idea of, astronomy in a way is detective work, right? Because it's not like we can just pour our stuff in our beakers and see what happens, right? We don't have a laboratory. Our laboratory is the cosmos. And I think that's sort of very, you have to be very creative in astronomy. And I think that's something that really made me, that made me get into it, and that made me stick around in the end for as long as I have.
What I find interesting in your account is another parallel to what Jana said. I mean, in Jana's case, I believe it was a school teacher. In your case, it was a university teacher. But the impact that a really good teacher can make, I think that's I know that from my own path to astronomy. So I think that's a really amazing thing. So, okay. So after this first panel, we'll head over to Lucian and his talk, which hopefully we can, yep, there I see.
Enjoy.
So how do we find life on other planets? So the stage is yours.
Thank you very much. So that's what I'm going to be talking about, and apologies for the technical difficulties, but I hope you can hear me fine now. I'm going to talk about a project that I did about finding life on other planets. And like I've said, finding life on other planets is actually a really complicated thing, right? Because other planets tend to be quite far away. But it's actually also one of the oldest questions that we've been asking ourselves, right? You can look into popular media and there's films about aliens and books about aliens, and people have wondered, are we alone? Is there other stuff out there? But the problem is, if there was other stuff out there, how would we actually go about in finding it? Well, with recent developments in telescope technology, we've actually been managing to discover lots and lots and lots and lots of exoplanets. But the problem with all of these exoplanets is that they're really, really far away, as in not just the distance that we can, just fly a little rocket ship to. So we have to get a little bit creative about it. The good thing is that there's lots of these exoplanets, like I've mentioned. Today, there's over 4,000 confirmed exoplanets that we found. When I say exoplanets, that's a shorthand for extrasolar planets, meaning planets outside of our own solar system. So, not Jupiter, but something like Jupiter maybe, but really, really far away. So if we can't travel there, what can we actually do to find life? We can use biology. As I mentioned previously, we're looking for life, and biology is just the science about life. So we'll look into our colleagues' sort of techniques a little bit and see what they do. When we think about biology, when we think about life, you may think about people, you may think about plants, you may think about little bacteria floating about the water, and there's lots and lots of different types of life. I'm not naming all of them obviously here, but what they all have in common is that they all metabolize. Metabolizing meaning that they consume something and in return they produce something else, and they gain energy from that process. So for humans like you and me, we eat food, we breathe in oxygen, and in turn we breathe out CO2 or carbon dioxide. Plants are a little bit different. They use a process where we call photosynthesis, where they take in light and they take in CO2 and they breathe out oxygen, so to speak. And bacteria actually have lots of really complicated and different types of metabolisms. But one type of bacteria that I want to look at more closely with you here is a type of bacterium called a methanogen. And that methanogen consumes hydrogen and CO2, and in return it produces methane, which is why we call them methanogens, which just means a methane producer. And methane is actually a really interesting thing that I want to talk about a little bit here, and that's actually very useful for us in astrobiology, because methane, unlike a lot of other gases, is very much principally produced by life. So if we find a lot of methane somewhere, we can generally assume that it's got to be made by life, because there's not that many other things that actually make methane. Unlike, for example, oxygen, unlike, for example, other gases that we might find in the atmosphere, like nitrogen. Nitrogen doesn't need a biological process to be produced, but methane generally is produced by biology. So what happens is, if we're looking at a planet, an exoplanet, for example, and we've got these methanogens on there, well, they metabolize, they eat, they grow, and they produce methane in that process. And if we were to have lots and lots of these methanogens, we'd also get lots and lots of methane in the atmosphere. But how is that actually helpful to us? So we've learned that we can get methane in atmospheres of exoplanets that might have lots of these methanogens, but it's still not like we can just go there and get a sample of the atmosphere to test it for methane. So what we do is we use a very handy tool called spectroscopy that physicists use in all sorts of areas. And if you know a little bit about spectroscopy, if you know a little about light, you might know that light is made up of actually not just one color, but light from a star is made of lots of different colors in varying proportions. Or we also in science sometimes say they're made of different wavelengths. And when that light from a distant star, so I've made a little sketch here that's not actually very scientifically accurate, but I hope you'll forgive me. When the light from that star that's made up of lots of different wavelengths comes through the atmosphere, comes to Earth from that star, there's a good chance that some of it passes through the atmosphere of the exoplanet that I've sort of marked here in a little blue circle. So what happens to the light when it passes through the atmosphere? Well, if an exoplanet doesn't have much of an atmosphere, a very thin atmosphere, the light just sort of passes through, nothing much happens with it. But if there's special gases in the atmosphere, like, for example, methane, there's a really interesting thing that happens, and that is that methane, or that other gas that we might be speaking about, absorbs certain colors of that light. So it doesn't necessarily absorb all of them, but it can absorb certain colors. So in this specific sketch that I've done here, the methane is absorbing the purple light and the yellow light. And that's actually really important to us. Because then when we on Earth look at the light from that distant star and we look at the different colors, we might notice, oh, there's no purple and yellow light in there. So there has to be methane in there that's absorbed all of that purple and yellow light, right? In reality, it's a little bit more complicated, but that's the basic process. So if you see in reality, it's less of a binary thing. There's no light or there is light. It's more like the more methane we have, the more of that light gets absorbed. So if we have very few organisms producing only a little bit of methane, you might actually get most of the purple and yellow light still coming up over to Earth. But if you have lots of these organisms and lots of methane in turn, you get much less of that purple and yellow light, up to the point where you'll barely see any of it at all. And this is obviously a very simplified sketch here. What it actually looks like more in science is that the methane absorbs specific wavelengths of what we call a spectrum. So the way that it looks is generally the more methane we have, the deeper that hole in the spectrum is. And I've actually made a little simulation of a spectrum here. So this is actually the spectrum of our own planet Earth, as seen by a certain telescope if you were to go quite far away. So as far as we might be to an exoplanet. And we can see here in blue, we've got the line of no oxygen being present in the atmosphere. And the red line signifies actually present atmospheric levels, or PAL levels of oxygen, which is about 20% of the atmosphere. And you can see actually quite clearly around here that compared to the no oxygen case, the oxygen case has a very deep sort of hole in the spectrum. And that's exactly what we're looking for when we're looking for what we call a biosignature. So a signature of a gas in the spectrum that signifies a biological origin. This is obviously a very nice spectrum. And if you were to look at the spectrum that I actually made, there's noise there, there's lots of different stuff happening. But what we generally can see, and that what I was talking about earlier as well, is that the more of a gas we have, so for example, here you can see the blue is the baseline of methane, so very little methane, which might be just a few organisms on that planet, compared to on the left panel here, 1% of methane, and on the right panel, 10% atmospheric methane. So 1% of the atmosphere being methane, or 10% of the atmosphere being methane. And when you compare the two of them, you can actually see quite clearly that the more methane we get, the bigger these holes in the spectrum get, and the more clear the signature is. So ideally, we'd want planets with lots and lots of biological activity, because it'll be much easier to detect that biological activity. Now, if that all was a little bit fast, I'll present a very brief summary to you guys. What we know is organisms metabolize, and when they metabolize, they produce gases. And these gases in an exoplanet can then gather in the atmosphere. When the light from the host star that the planet goes around passes through that atmosphere, some of that light is absorbed, generally specific colors or specific wavelengths. That light is then missing from the spectrum that we can see on Earth with our telescopes. And the deeper the hole in that spectrum is, so that trough that I've been pointing out to you, the more gas there is. And the more gas usually means there's more life on that planet. Thank you very much for that, paying attention.
Okay, thank you, Lucian, for that really, really nice talk. I always love it when there's these personal drawings, because it's very clear. You only focus on what we need to know. And so let me see. There are some good vibes in the comments. And there is somebody saying a good astronomical lecture. That might have been the one before. I actually don't know. But there's no specific questions. So let's just get the others back in. We've heard a little bit about aliens in various contexts. We have heard about the aliens who could watch our own galaxy from a distance and tell us potentially about our past. We've also heard about the bacterial aliens, mainly, who, by producing methane, might actually help us detect them without meaning to. So a question for all of you. We are not going to go very far in the direction of aliens, but if humans were contacted by an alien species and they were really advanced scientifically, and of course they would be very busy and they wouldn't have much time for humans because we are a little bit backward in so many ways. But you just happened to meet one of them, and she told you that you were allowed to ask one scientific question, and they would tell you this very advanced answer. So let's keep it to astronomy, but which question would you ask those advanced aliens? Or a little bit more abstract, what is sort of the single thing that you most want to find out about astronomy? Maybe let's start with Jana again.
Yeah, this is a very tough question. There are so many questions in astronomy. I think there may be two questions which I think would be really interesting to find out the answers.
You want to bargain with that alien, okay?
Yes, I want to bargain. I want to get 2 answers. Yes, one of the questions which I'm very interested in is how fast dust grows in the galaxies and why. Because in my observations of very distant galaxies, what I find is that they have a lot of dust. And we know that the stars are made of just like the first stars are only made from hydrogen and helium. So all the elements are just coming from burning of these elements in the stars. And by already very fast, as there's so much dust in the galaxies, I think this would be very interesting to know how galaxies acquire a lot of dust and very fast. And the other question, which is not very related to my research, but I think it's a very burning question for everybody, is what dark matter is made of.
What is dark matter made of? Yes. So I think when this leaks to the media that you had this opportunity to ask this advanced alien a question and then you wanted to know about dust, I think that takes a little bit of explaining, but I think there's a serious and interesting issue there, which is sort of the gap between what we do in our science in practical terms and those very outreachable topics that if you ask somebody on the street what they care about in astronomy, what they talk about. So I think it's interesting that you would use one of your half questions, let's say, to learn about dust. And I think the interesting bit is that shows what the perspective is for where scientists really think that they can advance their knowledge, and which is not always the same. That again, as a person on the street, you would think to ask about astronomy. So Gregor, dust and dark matter are already taken. So what is your question?
Actually, I would ask an engineering question. I would ask how you go faster than the speed of light.
Oh, because that alien has obviously reached us in some way.
Yes.
Yeah, that's a good one.
And you don't believe her generation starship is parked in near Earth orbit, which might be how she got here. So she's never seen her home planet. Everything that she can tell us about her own past is from the ancient records stored on the generation ship,
or it is an artificial life form, which might be where we are going. So maybe
that is quite possible. But no, interesting that you would ask the engineering question. And of course, if you get a sensible answer, then that would abruptly transform astronomy into, and not only astronomy, into a whole different kind of science. We've learned a little bit about all the passive analyzing, passive spectroscopic analyzing that we do. But yes, that would make a huge game changer.
I think it would be a very complex answer that the alien might be too annoyed with the question to answer it. So,
or maybe that's why you only had a single answer. So
yes. So if I would ask something about astronomy, I would probably ask about cosmological questions, or I would ask if our current cosmological model or our understanding of dark energy is approaching what they think.
And the alien would probably answer, do you humans even have an understanding that sort of deserves that particular name? Because, I mean, dark energy for us is mostly a single parameter, right? I mean, sort of.
Exactly. For us, it's
Up in
just a
there.
constant, or it could be something which evolves due to a very simple equation of state. But it's we have no idea if it's a field in some form, or if it's just related to a parallel universe which is kind of interacting with us. It's really
We have aliens, and now we have the parallel universe. So we're really going there. Apparently.
So lots of opportunities to confuse us.
For everybody out there listening, so I think this was briefly mentioned in Gregor's talk, because that is obviously what Euclid is also meant to research. But this was about dark energy, so about the fact that we did discover that not only is the universe expanding, not only are all these distant galaxies moving away from us, but in addition they are, and this was briefly mentioned, they're moving away from us in an accelerated fashion. So as we wait over time, that expansion gets faster and faster. And the question, of course, is what is driving that acceleration? What is the cause for that acceleration? And right now, the only answer that cosmologists have, the only mainstream answer, let's say, I mean, there's sort of people nibbling at the cutting edge of research, obviously, but right now the only answer is that, okay, we can add a parameter to our equations, and with that parameter and a certain value for that parameter, we can explain the observations of expanding of the accelerated expansion. But it is really not much more than that, is it? And
the frustrating thing is,
sorry, yes.
The frustrating thing, I suppose, is that everyone hopes for something more interesting, but it seems a single constant seems to work out very well with observations.
And apparently the story is true that the name dark energy is actually, in a way, a political maneuver, right? So, that name was actually invented, so it replaced the cosmological constant, and it was invented explicitly with the potential of funding by the US Department of Energy in mind, because if it's dark energy, then it falls into the realm of the Department of Energy, and that successfully led to the financing of what is now WFIRST, or well, now the Roman Space Telescope, which I believe is still financed in part by the US Department of Energy. So the power of public relations and the power of naming, if you will. So
don't tell all the secrets.
I'm sorry, we're being very honest here, and I think the Department of Energy knows by now, so because that secret has been out for a long time. Okay, so Lucian, speaking either for yourself or for those cuddly little bacteria that were featured in your talk, you are meeting the alien. She asks, or she gives you the opportunity to ask one question.
So yeah, the issue that you're posing for me here is the first question I would ask is, are we alone, right? And that question has very much been answered by just her existence.
Again, so I mean, she would give you a long, patient look and leave, I think.
So I'm not going to
respond
my question on that, right? I think what I would ask about otherwise is actually about the fate of the universe and where it's all going to end up, right? Because depending on the dark energy that Gregor has mentioned, how much of that we have and how much dark matter there is, there's sort of different scenarios what's going to happen with the universe. And we've got an idea what it might be, but it might be that we're wrong and that a lot of theories are actually just not very good at all at the end, and there's something that we're missing. So I think I'd be really interested in knowing, and even if I will never, none of us are going to be around for that, but just what is going to happen to the universe? Is it going to implode back? Is it going to just keep expanding? Is it going to get ripped apart? Is it eventually going to just reach sort of like a steady state when nothing much is happening and all the stars die? I think there's a lot of sort of existential questions to be asked, and I'd be really interested in knowing where that part of our history is going.
Oh, definitely. And for the sake of our viewers, we should say that the standard scenario is comparatively boring, right? It's not the getting ripped apart. It's not the recollapse. It's just sort of expanding in an ever accelerated fashion, and as the universe thins out, the dark energy component becomes ever more important, which sort of circles back to Gregor's answer. And then I think the interesting bit is that at some point we are not even going to see very distant galaxies. So people will really need to rely on historical records in order to know what the universe is about. Also, the cosmic background radiation as sort of the afterglow of the Big Bang is going to have faded to even lower frequencies. So yes, I think, I mean, in a way, we live in an interesting time where you can actually do extragalactic astronomy and hope to find at least some answers, like Gregor, like your Euclid mission will do.
And of course, the matter that's close to us eventually will fall into a black hole. So it gets boring in two ways.
It's a very boring universe of just black holes and stuff in them, very far apart.
Yeah, I mean, black holes, as a number of people, including Stephen Hawking and so on, Werner Israel, have shown us, are the most boring objects that you can think of in a way. No more than 3 parameters, and we know that electric charge doesn't really figure into it. So, okay, so we have a very few more minutes left, so let's just have a quick lightning round. The alien obviously is not going to come, so, or at least we all hope that this might be the solution to our problems, but we are very likely on our own. So if you look back to what is really important for current astronomy, what we can hope to find, let's say, in the next 10 to 15 years. So do you have something that you're looking forward, or that you have a reasonable hope that we will find out that is interesting on those timescales? So Jana, do you want to start again, just very briefly?
Yes, I think I already mentioned in my talk that one of the interesting things which we really hope to find are the first galaxies, and we should wait for the results from the James Webb. But we also are going to be able to refine the properties of the galaxies which we already discovered, and we can also find some galaxies which are fainter than the ones which were discovered at these distances. And this will help us to get a more complete statistically picture of what was happening in these earliest times in the universe. So this, I think, my idea of what the future will bring us.
That sounds certainly realistic. Certainly we are all crossing our fingers on, when is it? Is it the 18th of December? When does the James Webb Telescope, when is it meant to start? Something along these
Like
lines. So
December. Mid to late December, if I remember correctly.
Yeah, something along those lines.
It's
currently on a very secret ship being shipped to Kourou spaceport. So, and they actually keep the secret because of pirates, actually. So now we have not only aliens, but also parallel universe and pirates featured in our talk. So I think we sort of are going through the astronomy bingo at a very quick rate. So we only have a few more minutes for Gregor and Lucian to just tell us very quickly what you hope to learn over the next 10, 15 years, just very, very quickly.
Well, I do actually hope we get a little bit more understanding of dark energy and if it's really a constant or not. Otherwise, maybe on the more short term, we make an advance is understanding how black holes grow in the early universe. So I think there's a realistic chance to get more insights. And they're not really that boring. They're actually fascinating objects.
Yes.
Oh, I mean, boringness is in the telescope lens of the beholder, obviously.
Yes.
So, okay. And so Euclid is still scheduled for launch in late 2022. So
January 2023 now. But it might, so according to what I understand, so there was a problem. Now it looks like this problem can be solved without further tests. So it's unclear whether they advance the timeline again to December or late 2022, or they stay with January 2022.
Okay, and then we might actually learn something about dark energy. Lucian, so closing words, basically, what do you hope to learn in a single sentence?
Yeah, I'm obviously also very excited for the James Webb Telescope, but I'm even more excited for there's new spectroscopic instruments, really good ones, planned for launch in about 2030, 2040, that are actually the ones that I investigated in the little graphs that I showed you earlier. So I'm really interested in the good new telescopes that will actually allow us to maybe find those methane signatures.
Okay, and that would mean the way of
Hopefully,
two very momentous things. One is that we are going to have some evidence of extraterrestrial life, and the other is that maybe we would find a spectrum on the title pages of all newspapers worldwide. I think that's, speaking from a public relations standpoint, that is something that would be something really extraordinary all on its own.
I would love to see that, yeah.
Okay, so we have now reached the end of our hour. So thank you very much for joining me here. And for all of those watching, on the Facebook page of the Office for Astronomy Outreach, for instance, you can find, or you should be able to find, what's up next for the 100 hours. So the 100 hours continue, I think, until October 4th. So lots of different offers from lots of different locations around the world. So thanks for watching, and keep looking to the stars, clear skies, as we say. Mostly in astronomers' circles, I think. In space telescopes, it really hasn't caught on, has it? But okay, so great. Thanks for watching, and we'll see you around in one way or the other.